dimension, we are able to derive sample complexity and generalization error bound for infinite hypothesis space. That means the basic dimension behaves like logarithm of size of this space. And then what kind of sample complexity or the generalization error bound can we get, right, based on basic dimension? Here are the results. So again, we consider like two cases. So first, we still assume consistent learners, meaning that although our algorithm uses an infinite hypothesis space, right? But when our algorithm is powerful enough such that given arbitrary set of training example D with m examples, right? Our algorithm can always find out a hypothesis from our hypothesis space, which is consistent with all the m training examples, meaning that the training error is 0. And then, if the number of training examples is bigger than this bound, we guarantee that with high probability, that is at least 1 minus delta, the generalization error of H is less than the designated level epsilon. So now this is a sample complexity for consistent learners with infinite hypothesis space. So if you contrast with the sample complexity for the finite hypothesis space, the bound looks pretty similar, right? Except that we changed some constant factors and also replaced the logarithm of size of hypothesis space by this basic dimension. Any questions so far? Everyone is good, right?
I'm almost scared to ask, but do you know why there's a 13 in there?
I don't either.
Okay.
So I can tell that generally how they obtain this. So this is just some classical results from computational learning theory. So the majority part of computational learning theory is to use all kinds of probability inequalities, all kinds of inequalities, and just embed them and use all kinds of tricks and to build a long chain and finally end up with this. And I need to mention one point that this bound is not very tight. So that's a pretty season for always for the computational learning theory. That means they can always they always lack of very tight estimation of those bounds. But at least these bounds can give you some insight. Right? For example, we know that how the Occam's razor appears again, right? So if your learning algorithm chooses a more complex model, that means more expressive hypothesis space, then to guarantee the same error level under the same confidence level, the number of training examples is more, right? It also reflected in space dimension. So this is for consistent learners. And we also have results for agnostic learning. Agnostic learning that although like infinite hypothesis space looks like very large, right? But it is also possible that there's an overlapping part between the family of target functions, this concept class, and the infinite hypothesis space. And then we would like to say on the agnostic learning setting, your learning algorithm chooses the infinite hypothesis space. What can we say about the generalization error? So here's the generalization error bound. So basically, if we have m training examples, then with high probability, 1 minus delta, the true error, that is the generalization error of our learned hypothesis H, with training error here, can be bounded by this. That means the generalization error is upper bounded by the training error plus a term, which is determined by the basic dimension of the hypothesis space your learning algorithm uses. The number of training examples and the confidence level. That's the generalization error bound for infinite hypothesis space. So now let us look at this bound and say what kind of insights can I get? Do we have the same kinds of insight for the final hypothesis space? So first, what if we increase the number of training examples? What will happen? An idea?
You expect your upper bound between two errors should shrink.
Yes. Then what does it imply? An idea, just a guess. An idea? Okay, let us look at together, right? So this inequality just states, okay, the true error is bounded by the training error plus this term, right? So if the number of training examples is large, then this term in the upper bound decreases, right? Why? Because the numerator is m, right? And the numerator is logarithm of m, and denominator is m. So we increase m, obviously the denominator increases much faster, right? So basically this term just decreases. That means the difference between the true error and the training error gets smaller, right? That means if we increase the number of training examples, then our true error is closer and closer to the training error, right? In a limit case, right? If you have the fixed this dimension, in a limit case, if you use like numerous training examples, then the true error is simply equal to the training error, right? So that's very intuitive. That's very natural. So the more training example you use, its training error can better anticipate its true performance, right? That's one point. Another point is that how about we fix the number of training examples and we choose different VC dimensions. Meaning that we choose different hypothesis space with distinct VC dimensions. So what does it imply if we use larger VC dimensions? An idea?
Difference in two errors should be bigger.
Yeah. If you use larger VC dimensions, we say this term. So although this is a logarithm, 1 over VC dimension, right? But if you increase this dimension, obviously this term will increase. That means your upper bound increases, right? Meaning that it's more likely your true error is far away from the training error. Then your true error is more risk to has more risk to be worse, right? That's how the Occam's razor's principle is reflected again. So if you have like two learning algorithms, right, and both learning algorithms achieves exactly the same training error, and which learning algorithm would you like to choose? Which algorithm would you like to choose? An idea? The smaller what? Yeah, to be more like rigorous with the smaller VC dimension. Right? When two hypothesis spaces are both infinite, you can now say which one is smaller, which one is larger. So we can only compare their the VC dimensions. And then, like if two learning algorithms, say one is like linear classifiers and the other is like a 100 layer deep neural net with 1 billion parameters. Both both models have the same training error. Now which one would you like to choose?
Simpler.
What?
Simpler one.
The simpler one, right? The linear classifiers. Why? Because linear classifiers has a much smaller basic dimension. So you can imagine that from this generalization error bound, you know that the true error is very close to the training error. Otherwise, if you use over flexible models, which is too flexible, it is likely that your true error is far away from the training error. It could be like a training error plus a big value, right? I'm not sure for that. So again, from this generalization error bound for infinite hypothetical space, we can justify Occam's principle again. So any questions so far? Everyone is comfortable? Okay. So now I want to remind you the importance of computational learning theory again, although this is not our primary focus. Right? We just introduced the basic concept and path vulnerability and where does the sample complexity bound means, what kind of what does generalization error bound reflect, right? So but I still want to emphasize it is the development of computational learning theory stimulates many important and powerful learning algorithms, right? So the first example is the boosting algorithm. So how was boosting algorithm proposed? The theoretical guys want to address the problem that whether a weakly learnable concept class can induce a strongly learnable concept class. Right? That means how can we combine a set of weak classifiers into a very strong one? And theoretically speaking, it is doable. And then people try to develop a practical algorithm to verify the theory. That's how boosting was invented. And now we'll introduce another very important result from computational learning theory. That is the generalization error bound. So from generalization error bound, we know that we can bound the true error by the training error plus the term determined by the confidence level, right? Because this is a probabilistic bound and this dimension. And then those smart people immediately thought about that. Can we use this definition to define a learning algorithm directly? So obviously, I want to design our learning algorithm to tighten this bound, right? To make this bound as small as possible. This procedure leads to the so-called structure risk minimization principle, and the prominent example is support vector machine. So we have introduced the prerequisites for support vector machines. So now, from today, we're gonna focus on support vector machines, a very fundamental, important, classical learning algorithm for linear classifiers. I will spend quite a few lectures on this topic. It is not only because it is so fundamental and connecting like the computational learning theoretical world and practical world, but also it is extremely useful and very widely used. So I can tell you, like, support vector machines are used much more widely than neural networks. Actually, in the future, if you are some data scientist or you want to use machine learning to address your practical problems, you will find that 95% of jobs can be well done by support vector machines. You actually have some much less chance to try deep neural nets. The reason is very simple, because not all companies will give you like hundreds of thousands of GPUs, and also not all companies can give you like terabytes of data. In most of the cases, I just gave you like 100 examples, 200 examples. And it will spend you like 3 months to get labels for those data. And then your boss will require you to build the classifiers immediately. And you'll find that small vector machines is more than sufficient to do that. So actually, because this is a central role of small vector machines, so I believe every machine learning person should be familiar with the basic concepts, the ideas, the techniques of small vector machines, because they're more general than small vector machines itself. In the future, if you want to develop your own learning algorithms, you can use those ideas again and again. So let us first look at the big picture, right? So before we dive into the details. So right now, our general topic is linear models. Of course, our primary topic, the entire topic in this class is supervised learning. Right? And we introduced the first type of classifiers, that is decision trees, which are not linear classifiers, also boosting ensemble of non-linear classifiers, and then we turn to linear classifiers, or linear models. Right? And then, based on how can we evaluate a learning algorithm, the goodness of learning algorithm, right? We first introduced the perception. Why we introduce perception? Because perception is a typical heuristic-driven learning algorithm. Right? When you conduct perception learning, it only updates when it makes a mistake. Right? If there is no mistake, it just skips. It's kind of lazy updates. And the less number of mistakes the perception make, the better the perception you have. Right? So this is the first type of learning algorithm, perception. And actually, perception has a sibling called Vino, which is it's not variant, and we'll cover in this lecture. And then we also introduce basics about the computational learning theory. We introduced the concept of PAC, probably approximate correctness, right? Agnostic learning setting, consistent learners. Right? All those theoretical framework actually wants to characterize what's the generalization performance of your learning algorithms. That's the motivation of the computational learning theory. So in addition to answering this question, right, these principles and this framework also motivates the small vector machines. So small vector machines, in more general, can be considered as an instance of the risk minimization principle, which we'll cover at the end of this lecture. So this is our big picture. Just keep it in mind, so feel that we are learning everything in an organized way, not just learn the classifiers and implement it and throw it out. So all those algorithms, all those models are connected. They are put in your knowledge base in a very organized way. And of course, based on the same paradigm, you can propose the new framework to evaluate your learning algorithm theoretically, right? And also you can use your theoretical framework to invent new type of learning algorithms. So this is the outline of our whole simple vector machine topic. So each topic we might need 1 or 2 lectures to cover. So it's a very long topic. First, we would like to introduce the learning principle of simple vector machines. That is maximal margin principle. So previously, we briefly discussed when two linear classifiers can both perfectly separate the data, right? Which one should we choose? And we all know that intuitively we should choose the one with the larger margin, right? Now this is just an intuition. How can we justify this intuition? Can we use the generalization error bar to justify this intuition? The answer is yes. And we'll explain why. justified with the computational learning theory. And then the SVM objective is just such kind of objective function which reflects the maximal margin principle. So next step, we'll introduce the objective function of support vector machines and how we simplify the objective function design. It's very smart and elegant idea. And once we have the objective function in hand, the learning procedure turns out to be an optimization, right? We are minimizing the objective function or maximizing the objective function to obtain the optimal model parameters. This is a learning procedure. And we'll introduce a very simple, very useful optimization algorithm called stochastic subgradient descent. Why we use subgradient? Because there's no true gradient. The objective function of support vector machines is not differentiable. But we can use subgradient descent. And then this is a large topic. The last topic is a large topic. So whenever when we discuss support vector machines, it sounds like it's not a simple linear classifier. So it's actually a highly nonlinear classifier. And how can we achieve this? How can we enable support vector machines to perform nonlinear classification? That will use the so-called kernel trick. And also, only the kernel trick won't be sufficient. We need to use some optimization knowledge to convert the objective function in the primal domain to the dual domain. Only in the dual domain of support vector machines we can apply kernel tricks and then perform nonlinear classification. So this is a large topic. Only understand this topic, you will be able to implement the most popular support vector machines. And then you will see why it is called support vector machines. What do the support vectors mean? So this name actually sounds weird. It will sound weird to you if you don't know the dual representation for support vector machines. So this is our whole plan. So first let us look at the learning principle of support vector machines. That is by maximizing the margin. Like how does it come out? How is it justified? So first, let us look at what the theoretical result kind of like this. Right? So we know from infinite hypothesis space, and the generalization error is upper bounded by the training error plus this term in terms of number of training examples and the basic dimension of the hypothesis space your learning algorithm uses. As an example for basic dimension, we just mentioned, right? For a linear classifier in the d-dimensional space, that is the hypothesis space of all possible linear classifiers that deal with d-dimensional input vectors is d plus 1. Then to get the generalization error bound for arbitrary linear classifiers, we can simply plug in. We simply substitute this d plus 1 for this dimension to get the generalization error bound. But that leads to a problem. Sounds like no matter what kind of learning algorithm uses, your generalization error bound is fixed, right? Because we just mentioned, right? The basic dimension for the linear classifiers in d-dimensional space is simply d plus 1. So no matter what kind of learning algorithms you use, you get the same generalization error bound. Looks like there's no room to improve your learning algorithm. Is that true? Is that true? Can we simply apply this basic dimension into this generation error bound, and then we're disappointed, right? We say, okay, there's no need to do any efforts because all linear classifiers will end up with the same generation error bound. Is that true? Or in other words, are all linear classifiers in a d-dimensional space the same?
What about the training error? If that differs?
Yeah, suppose like their training error are the same, at the same level. There's no dramatic difference between the training error if you use the same type of learning algorithm. Any idea? Any guess? Yes or no? Just one guess.
No.
Why?
Classifiers with a higher margin, you would expect better generalization error.
Yeah, your point is good. Yeah. But anyway, you can think of if it is known, then why do we proceed? Right? Why do we continue? There's no need for us to discuss like support vector machines. Right? Why should we allocate support vector machines? So obviously the answer is no. There's still room to improve the linear classifiers. The key insight here, the key point here is that if you apply this d plus 1 into this generalization error bound, you're assuming your learning algorithm is always searching over the entire hypothesis space. Because this is a dimension for the entire space of d-dimensional linear classifiers. So what if we restrict our learning algorithm to search just a subset of linear classifiers? You can imagine like we can partition this entire space into many subsets, right? And we let our learning algorithm just search over one subset. Then the actual basic dimension of the basic dimension, the actual basic dimension of the subset could be much smaller than d plus 1, right? In other words, if you can identify the actual subset of linear classifiers your learning algorithm search over, you can tighten the bound. Right? So this is the idea. If you still like use the this dimension of the entire linear classifiers in the d-dimensional space, well, you can now see the difference, right? But now, if you can look into your learning algorithm like in a more fine-grained level, you know that your learning algorithm won't like blindly search over the entire space, just restrict it into a small expressive subset. Then the actual basic dimension becomes smaller. Then we have a chance to reduce the generalization error bound. So everyone is comfortable at this point, right? Okay. So now the question is that how can we define subset of linear classifiers, right? Subset of hypothesis space. How can we define subset of linear classifiers? How can we characterize them? That reminds us the concept of margin. So let us recall the definition of margin. So what is margin? Yeah. So first, the margin is defined for the first version of margin. It's defined for a particular hyperplane for a particular data set. So if this particular data set can be perfectly separated by this particular hyperplane, then we say this hyperplane has a margin, and the margin is defined as the closest distance between all the data points and this hyperplane. Right? This is the definition of margin.
So we're assuming that everything is perfectly
Yes.
linearly separable.
Yes. If this data set cannot be linearly separable by this hyperplane, then this hyperplane does not have margin for this data set. This is a very important concept. So I put one question in the homework 3 to remind you this starting point. Don't try to like give you a set of data points, one hyperplane, just compute the smallest distance. When there is some prediction error, then there's no margin for this hyperplane on this data set.
So for two-dimensional data, it seems pretty easy to visualize if you can have a margin or not. Is there a trick for reducing higher dimension data or getting some type of statistic that will force us in the direction if that data set's literally separable?
Yeah, that's a very good question. That's actually a topic. It's called dimensional reduction, and there is a very classical model called LDA and do this kind of things. Projecting the high dimensional vectors onto a low dimensional space, typically in one dimensional space, to show that whether they're linearly separable. But this is not. This is not the motivation for we to introduce the margin. When we introduce the margin is to define different subset of linear classifiers or different subset of.
Does that process tell you what the hyperplane is? If LDA, is that what you call it? Does that sort of tell you if it's linearly separable? Or will it tell you like what the hyperplane?
It just to tell you what is the best projection on low dimensional space. When you project it onto low dimensional space, you're able to visualize them and see whether they can linearly separate. It cannot tell you whether they can linearly separate. In practical, especially for high dimensional data, there's no guarantee. There's no guarantee that your data is linearly separate. You can only test them, say you can run a perceptron, right? Or see whether the perceptron can finally end up convergence. If you convergence, good. Their probably is linear separate.
Okay, so if there's a positive and the negative sign, or a negative and a positive side, we can't have a margin.
Yeah.
But we still can have a hyperplane.
Of course.
Okay.
Hyperplane is here.
And then is the margin, is sort of the intuition behind the margin that it's a measure of how separatable the data is?
Yes.
Like, okay.
Yes. So you can say, if the data is not linearly separable, what's the meaning for margin? Meaning, margin defines the separability, the linear separability of the data set. If the data is not linearly separability, there's no reason for margin to exist. Okay. And then let us review our analysis, right? How we choose the linear classifiers, right? So we look at these graphs before, right? So suppose there are like positive examples here and negative examples here, and we find two hyperplanes, both perfectly separates the positive examples from negative examples. Then which one should we choose intuitively?
Each one, since the margin defines a larger, since the margin is larger, defines the data as more separable.
Well, we can say, okay, given the data, the separability is there, right? It won't change. But why we should choose a classifier, a hyperplane, with larger margin rather than smaller margin? We give very a rough and qualitative analysis, right? Remember?
If any of the data points deviate from like on the real data, they're less likely to cross that hyperplane as a larger dimension.
Yes, exactly, right? So it relates to a distribution of data, right? So you can imagine the dense regions where the training examples appear correspond to the high density regions. So you can say, okay, because positive examples are surrounded here and negative examples surrounded here, so we can roughly draw their high density regions. So the larger the margin your hyperplane have, the farther away your classification boundary from those high density regions. On the contrary, if your margin is small, then you are very probably to cross the high density regions. So what's the disadvantage if you happen to cross the high density regions? What's the consequence? What is the possible consequences?
Well, if you can happen to get points along that entire boundary for your training set, the testing set might have those, and you just classify something.
Yeah, exactly, right? Because, H2, so I like to plot it here. So, H2 cross the high density region. So it's very likely that the training example with the same label oscillate around classification boundary, right? Because here, the high density region for positive examples here is also high density region for positive examples. So for the next training example, it's very likely to appear here. If it appears here, H2 makes wrong prediction. And similarly, if negative examples appear here, H2 makes wrong prediction. Because it just crosses the high density regions, right? You have no guarantee that the same number of examples will always appear on one side rather than the other side. But if you have a large margin, you know that this boundary is far away from the high density regions from both negative and positive examples. So it's very unlikely that there's a positive examples here, right? Unlikely that there's negative examples here. So you can say, intuitively, larger margin classifier has low risk to make wrong predictions because it avoids high density regions. But how can it be justified? How can it be justified more rigorously? How can it link to the computational learning theory? Let us get back to our BC dimension. So, as we previously mentioned, right, if we use the entire space of linear classifiers as our hypothesis space to search over your generation error bound will never change, right? It's just a loose upper bound. You cannot see anything. But if we can define some subset of linear classifiers, then the basic dimension of the subset of linear classifiers will be reduced. Now, how can we define them? We can define them according to the margin. This is called data-dependent basic dimension. So suppose we consider linear classifiers with margins gamma 1, gamma 2 for the training set. Right? So that's why it's called data-dependent, because this set of linear classifiers depends on a particular training data set. So we define each one a subset of linear classifiers to be all the linear classifiers that have a margin for this training set at least gamma 1. And correspondingly, we have H2 that consists of linear classifiers that have a margin at least gamma 2. And gamma 1 is bigger than gamma 2. So now you can tell me overall which subset of linear classifiers or which hypothesis spaces are better in terms of the generalization performance. Why? Yeah, according to our analysis, right? So because on average, the classifiers in each one have a larger margin than the classifiers in each two, because gamma 1 is bigger than gamma 2. So we expect that the entire set of functions H1 is better. And this intuition can be proved or justified by this theory. Proved by Vapnik. Vapnik is the pioneer in the computational learning theory and theoretical machine learning. Right. So what does this theorem tell us? So let H be the set of linear classifiers that separate the training set by a margin at least gamma. So you can say this is exactly how we define H1 and H2, right? Data dependent is dimension, right? Let H be the set of linear classifiers that separate the training set by a margin at least gamma. Then we can claim that the basic dimension of this set of linear classifiers H is upward bounded by 1 plus minimum of R square or gamma square and D. So D is the dimension of the input vectors. And R is the maximum norm of the input vectors. So geometrically, you can imagine if you draw a circle or sphere with radius R, then this sphere will include all the input vectors. That's what R means. So if you still have impression about perception, what does this term mean? R square or gamma square. I heard the maximum number of mistakes made per perception, right? If of course, if the data is linear separate, so it's kind of it's kind of a surprising coincidence here. Right? But here we have a completely different meaning here. So basically, for a data-dependent hypothesis space H, that is the margin of the linear classifiers in H, at least gamma, we can bound the basic dimension of H by this 1 plus minimum between R square or gamma square and the D input dimension. So gamma is the margin. So now let us compare like basic dimension of H1 and H2 here. What can we get? What does it imply? For H1, because the margin gamma 1 is larger, so the basic dimension of H1 has a smaller upper bound, right? Similarly, so basic dimension of H2 has a larger upper bound. So it's more likely basic dimension of H1 is smaller than basic dimension of H2.
Does it depend on B?
Yeah, of course.
If DC input, you cannot see this.
Yeah, yeah. So this is a justification, it's not a rigorous proof. Like you must be better than that. You can say even in the computational learning theory, we can now say, okay, the algorithm can always give you like 0.5 true error, right? I can also give you like it guarantees at least 90% chance it's 0.5. So here, same thing. It's not like a deterministic conclusion. You just through this bound and tell you why H1 is better than H2. Because the basic dimension of H1 is smaller. It's more likely to be smaller, not deterministic to be smaller. So now this is our chain to reason, right? So larger margin for your hypothesis space, that means the lower basic dimension of your hypothesis space. And the lower basic dimension of your hypothesis space leads to a tighter generalization error bound, meaning that you're more likely to have a smaller generalization error. So everyone is comfortable at this, right? Any questions so far? Okay, great. So now let us think about it. Right? So from this theory, what else can we get? What else can we think about? So can we use this theory to design some principle for learning linear classifiers? Based on the theory, right? Based on this justification, if you design a learning algorithm to learn a linear classifier, so how would you like your learning algorithm to search linear classifiers?
Search for the linear classifier and give you the largest margin.
Yes. Exactly, right? So this stimulates the so-called max margin learning principle. That is, we want to design our learning algorithm to find a linear classifier that maximizes the margin. So you can imagine that if your hypothesis space now becomes the set of linear classifiers with the largest margin, then your VC dimension of this particular hypothesis space will be largest. Then you have the tightest generalization error bound.
You say that your space is the subset that all have those, so there's several that have equally high margin?
Yeah, it is possible.
Okay.
Even like just one is fine, because VC dimension can be defined on a finite hypothesis space as well. Any questions? So let me repeat again. So we're gonna we'll go to the next step. So looks everybody's comfortable with this. It's really very trivial, right? I think this is harder than decision trees. Why do you think decision trees are hard? Okay. So how does this maximal margin learning principle comes out? Based on this theorem, if we let our algorithm to search over just a subset of linear classifiers, the VC dimension of this subset of linear classifiers can be much smaller than the VC dimension of the entire linear classifiers. That's how we tighten the generalization error bound. That means that's the way we improve the generalization error. So now we change our hypothesis space, right, to be the subset of linear classifiers with the largest margin. We know from the theory, the larger the margin hypothesis space have, the smaller the VC dimension. So now you have the largest margin. You have the subset of linear classifier with the largest margin. Your VC dimension can be the smallest, right? Then you obtain the tightest generalization error bound. That is the best generalization error bound. That's how this maximum margin principle was motivated. So now our training objective is to find a linear classifier with the largest margin on this training data set, right? Then the question is that how can we turn this principle into some explicit objective function? Then make it feasible, right? Now let's go. So first, we need to record the geometry of linear classifiers. So our classification boundary is determined by an equality such that the classification function value is 0. And for arbitrary point in the data set, the distance between this point and this margin can be computed as the absolute value of the function, classification function evaluated at this point, divided by the norm of the big vector W. So this is a general definition between arbitrary distance and a plane, a hyperplane. I'll give the formula in the previous lectures. You can verify it. And during our prediction, we just compute the classification function value and take the sign. Right? An important property for linear classifier is that because we only care about the sign during the prediction. So no matter how you scale your model parameters, like say by 2 or by 100, by 1,000, by 1 billion, your linear classifier remains unchanged. Your classification boundary is here, never changed. Right? This is a very important property. right now, just keep it in mind. And now, let us look at how we turn the maximum margin learning principle into a mathematical objective. Right? So first, according to the definition of margin, which is the distance of the closest point from hyperplane, we can write the margin gamma as the minimum, right? Minimization over this distance. Right? And distance is between every training examples xi and the hyperplane. And here the numerator is yi multiplied with the classification function value. Why can we write it like this?
So this is where I get confused, since y can either be -1 or +1. Shouldn't this be
Absolute value?
absolute value?
Yeah. Yes, of course. But here we can simply write it like this. I want to ask you why. We can write it without any concern.
If yi is negative, then theta is below plane, so then the numerator is negative.
But this is distance, right? Distance cannot be negative.
Yeah, I mean, if yi is negative, the other can also be
Yes.
negative.
Yes, exactly, right? That's the definition. Anyone want to step in? Okay.
Well, and we can do that because it's a perfect linear classifier, right?
Yeah. We emphasize a lot, right?
So every time yi is negative, the other one will also.
We emphasize the margin is there only when the data is perfectly linearly separable. Right? That means if you use a linear classifier to predict every data point, you make a correct prediction. And then this production between the ground truth table and the classification function value is always non-negative. Right? And here the denominator is the norm of the weight vector. We don't need to explain more, it's just the standard formula. And then to maximize the margin, we just maximize gamma here, right? With respect to the weight vector and the mass parameter. And now we come up our straightforward formulation, right? Maximize the margin, and the margin is the minimization. So overall, it's actually a max-min optimization problem. Right? If you substitute gamma, if you substitute this minimization for gamma, right, your objective turns out to be a max-min problem. Right? And here I want to introduce some extra terms. So this margin, the original margin, is also called geometric margin. Why? Because geometric is a very nice view, right? It's just the distance. But we also call the numerator only as the function margin. So remember, functional margin is simply the production between the ground truth label and the classification function. So we use those two terms a lot when we illustrate supply-back machines. Keep it in mind. The difference is simply like geometric margin is simply the function margin divided by the norm of the weight vector. So although we can outright formulate our objective function as a max-min problem, it is problematic because it is hard to optimize. If you solve a max-min problem, you are not trying to find a local minimum, nor local maximum. You're trying to find a saddle point. So the computation is pretty difficult. Then a natural question would be, can we further simplify this objective? Right? We do not want to do a max-min. It's kind of weird optimization. How can we do that? Those people who develop the supply-back machines are very smart. Use the property we just mentioned. Right? Remember, during the prediction, we only care about the sign of your classification function value. We never care about the skew of those model parameters. That means no matter how large, how small you skew, no matter how you skew up or skew down your model parameters, the classifications, the classifiers are totally equivalent. So now, why not we just constrain our model parameters, the weights and boss parameter, to be some standard such that we do not need to compute this minimization operation. So the key idea is here, right? Because we have the freedom to scale up and down the weight vector W and boss parameter B's, we can just restrict them such that the functional margin, that is this term, is simply 1. Then the margin is simply 1 over the normal W. That's the basic idea. So now let us look at how we implement our objective function formulation, right? So remember, our all-right formulation of support vector machine objective is to do the maximum, to maximize the margin, and the margin is the minimization of all the distance between the data points and hyperplane, right? So it is originally it's a max-min problem. Now, because we only care about the sign of the classification function value, we do not care about the skew of W and B, we can intentionally set the absolute score, that is the function margin, of the closest point to be 1. And then the margin becomes 1 over the normal W.
So we're scaling W such that the top part of that is
1.
Is 1.
Yes.
And then we're checking the value of W.
Yes. Yeah. That's the key idea. So simply, because they are totally equivalent, right? So why not we search over all data points like xi, yi, right? And pick up the smallest one. We just intentionally set the smallest numerator to be 1. Right? And then the margin is simply 1 over the weight vector, the normal of the vector W, right? There's no minimization procedure. And then maximizing the margin gamma with respect to W and B is totally equivalent to maximizing 1 over the normal W.
Why you still have B?
Because you have a constraint that the closest point, the function margin of the closest point is 1. The numerator, the smallest numerator just be 1.
Yeah, to be 1, so the B disappears.
The B does not disappear.
It's not the boundary condition anymore in your maximum object shape.
It's not disappears. So let us see the next step, and you will see where is B. So okay, so everyone agrees that if I intentionally skew the model parameters W and B is such that the closest point, for the closest point, the function margin is 1, then our objective function becomes here, right? And then maximize 1 over normal W is equivalent to minimize its inverse, right? And we can multiply with a constant 1 over 2 here. So now it comes out our new formulation. So our objective function is to minimize 1 over 2 multiplying with the square norm of W, but we add constraint such that for every training example I, we have the function margin less than 1. You see, this constraint actually intentionally sets the smallest functional margin to be 1, right? Because for every training example, we have this function margin less than 1. The smallest margin should be 1, right? Smallest function margin should be 1. Any questions? Everyone is good?
Will you remind me what W transpose times W does?
Oh, it's square norm of W.
Square root?
Yeah, square norm of W. You can simply like take normal W take square is equivalent to W transpose W. So you maximize inverse of square norm, or inverse of norm is equivalent to maximize. Or you maximize inverse of norm is equivalent to maximum, equivalent to minimize the norm itself, right? And it's equivalent to minimize the square of norm. And you multiply constant 1 over 2 here. So essentially, the trick here is just like I put this, I use this actual constraint, right, to remove the minimization procedure to compute the margin, because you fix the function margin to be 1 over the norm W. We remove the minimization procedure. The cost is that we should add actual constraint. So again, here is just to remind you that this objective is to minimize. Minimize is equivalent to maximize 1 over the norm of W. And this condition is true for every example. That indicates that we intentionally set model parameters such that the closest points function margin is 1. So this is called hard small-back machine. Why it's called hard small-back machine? Because we require all the training data points is linear separable, right? If the data is not linear separable, what will happen? What? Well, I don't think it will go on for infinity. Because this is a kind of, we haven't talked about the specific algorithm. Yeah, it is infeasible. Why? Because you can imagine, right? So if the data is not linearly separable, then these constraints cannot always be satisfied for all the training examples. There are always exist some examples such that this function margin is less than 0. That means there is no feasible region. You cannot find any feasible point that satisfies this constraint. You cannot find any solution. So obviously, like hard SVM, although it's elegant, it's not very practical, because in practice we cannot guarantee that your data is always linear separable. So we need to modify this hard SVM objective function to make it more realistic. How can we do that? Let us discuss on Wednesday. I don't think you need to worry about that. There are no guarantees. But you need to be aware they're different. That's possible. Yes. you have if you want to form one, just one.
Yeah, I guess you'd rather it be here, right? It's like you should do that shit with That's kind of weird. Why? This whole thing about really, we're not concerned with the line, we're concerned with it's
So one thing is, this is supposed to be sort of 1 plus K.
no, you can generalize around it.
No, because you don't have to. Remember, what is the input vector?
Our equation.
Yeah, so what's the length of yeah, and R is the maximum length of the input vector.